What if I told you the air you breathe, the water you drink, the DNA inside your body, and even diamonds all exist because atoms learned how to share? But why would atoms share electrons in the first place? Why doesn't every atom just steal electrons like in ionic bonding? And how can something as soft as oxygen gas and something as hard as diamond both be created using the exact same type of bonding? Today, we're decoding one of the most important concepts in chemistry, covalent bonding. And by the end of this video, you'll understand why atoms form covalent bonds, how electron sharing works, single, double, and triple bonds, polar versus nonpolar covalent bonds, and why covalent compounds behave so differently from ionic compounds. Before we dive in, let's anchor ourselves in what we've already built. In Episode 1, we have seen that atoms bond to lower their energy, and the octet rule drives almost everything. Episode 2 explained about ionic bonding. Typically, metals donate electrons to nonmetals, creating ionic bonds. But what happens when neither atom is strong enough to steal? When the pulling power on both sides is roughly equal, that's where nature uses a different strategy. Instead of, take my electron, atoms say, let's share it. And that sharing creates a covalent bond. A covalent bond formed by the sharing of one or more pairs of electrons between two atoms, where each atom contributes electrons to the shared region and both nuclei are attracted to the shared electron density. Let's start with the simplest molecule in the universe, hydrogen gas, H2. Each hydrogen atom has one proton and one electron. It has room for one more electron in its shell. It needs two to be stable. Now here's the thing. Hydrogen's electronegativity is 2.2, identical to its partner. Neither atom can steal. They're perfectly matched. When they get close enough, their electron shells overlap, and suddenly, both electrons are attracted to both protons simultaneously. Both atoms are now experiencing the electron count of a full shell. Both feel stable. And here is the beautiful physics. Two positive nuclei, which would normally repel each other, are now both being pulled toward the region of shared electrons between them. The electrons act like a bridge, a glue named covalent bond. They hold the nuclei together. This is not a compromise of weakness. It's an arrangement where both atoms genuinely win. The system now has lower energy than the two separate atoms. And lower energy means greater stability, as we established in Episode 1. To represent these shared electrons, chemists use Lewis structures, diagrams that show every valence electron in a molecule. We'll explore those in detail in a separate video, but for now, let's focus on building a basic understanding of how they work. The rule is simple. Shared electron pairs are shown as lines between atoms. Lone pairs, electrons not involved in bonding, are shown as dots on the atom. In hydrogen gas, H2, one shared pair. One line. Each hydrogen effectively has two electrons. A complete shell. In fluorine gas, F2, each fluorine has 7 valence electrons. They share one pair, giving both a complete octet. 6 electrons on each atom remain as lone pairs. Sometimes one shared pair isn't enough. Take oxygen. Each oxygen atom needs 2 more electrons. So they share 2 pairs of electrons, forming a double bond. Double bonds are stronger and shorter than single bonds because more electrons are being shared. And nitrogen, one of the most dramatic cases in chemistry, each nitrogen has 5 valence electrons. They need 3 more. So they share 3 pairs. A triple bond, N2, is one of the most stable molecules in nature, which is exactly why 78% of our atmosphere is nitrogen that barely reacts with anything. And that incredible stability comes from its triple bond. The more electrons atoms share, the stronger and more stable the bond becomes. This is one of the most reliable patterns in all of chemistry. All right. Now there are 2 more important concepts you need to know: bond length and bond energy. Bond energy is the energy required to break 1 mole of a specific bond in the gas phase, and bond length is the average distance between the nuclei of 2 bonded atoms. Now, look at carbon-carbon bonds. A single bond has a bond energy of 347 kilojoules per mole. It takes that much energy to break it. Carbon double bond, 614 kilojoules per mole, nearly double the strength. Carbon triple bond, 839 kilojoules per mole, the hardest carbon-carbon bond to break, and as bonds get stronger, they also get shorter. Bond length of carbon-carbon single bond is 154 picometers long. Double bond is 134 picometers, and triple bond is just 120 picometers. The atoms are pulled closer together by each additional pair of shared electrons. Now that we've understood bond length and bond energy, let's take things one step further. These two ideas help us understand how strongly atoms are holding on to each other, but there's another fascinating layer: how those shared electrons are actually distributed between the atoms. This brings us to one of the most important concepts in covalent bonding: polar and nonpolar bonds. When two identical atoms bond, like in H2, O2, or N2, the electrons are shared perfectly equally. Neither atom pulls harder. The electron cloud sits exactly in the middle. This is a non-polar covalent bond. But what about water? Hydrogen bonds with oxygen, two atoms with very different electronegativities. Electronegativity of hydrogen is 2.2, and for oxygen it's 3.44. Oxygen pulls far harder on the shared electrons. A polar covalent bond is a special type of covalent bond where the electron pair is shared unequally due to a difference in electronegativity. The more electronegative atom gains a partial negative charge, and the less electronegative atom gains a partial positive charge. This polarity, this charge imbalance, is the reason water has extraordinary properties such as high boiling point, surface tension, hydrogen bonding, and its ability to dissolve more substances than almost any other liquid. The polarity of the OH bond is the origin of all of it. Now that we've understood polar and nonpolar covalent bonds, let's see why these concepts actually matter, because from the water in your glass to the DNA in your body, covalent bonding is working behind the scenes in almost every part of our daily lives. Your DNA, the molecule that carries every instruction for building and running your body, is a covalent structure. The genetic code is written in covalent chemistry. Diamond, the hardest natural material, is pure carbon. Every atom bonded to 4 neighbors by strong covalent bonds, extending in all 3 dimensions forever. There are no ions, no charges, just sharing, endless, rigid sharing. Graphene, 1 atom thick, stronger than steel per unit weight, one of the most exciting materials in modern physics, is also pure carbon. The same atoms with different covalent bonding geometry, a completely different material. Every drug molecule that has ever saved a human life, aspirin, penicillin, insulin, is a covalent molecule. Its shape, determined by its covalent bonds and electron geometry, is precisely what allows it to fit into the biological target it was designed for. Covalent bonding doesn't just explain chemistry, it is the chemistry of life. So today we discovered that covalent bonding involves sharing electrons. It mainly occurs between nonmetals. Bonds can be single, double, or triple. Covalent bonds may be polar or nonpolar. From the oxygen you breathe to the DNA inside your cells, covalent bonding is everywhere, and together with ionic bonding, we now understand 2 major ways atoms combine to build matter around us. So that's the magic of covalent bonding, the sharing that holds our world together. But what if atoms don't share, and they don't steal either? What if they all just throw their electrons into a common sea? That's where things get even more interesting. Next time, we'll explore metallic bonds, the reason metals can bend, conduct electricity, and shine like nothing else in the universe. If you enjoyed today's video, smash that like button, drop a comment telling me your favorite covalent molecule, and subscribe so you don't miss the metallic bonding video dropping soon. Turn on the notification bell. Trust me, you don't want to miss how metals get their superpowers.